the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 83, where today for the very first time, we don't really have an episode.
That's not true.
Instead, no. I was gonna come into it. No, we don't really have an episode. Instead, it's gonna be a discussion.
Yes.
A math and physics discussion between yours truly and him. We're going to be just talking today, and I think we can maybe see this in the future. Who knows? Always just a nice breather from the stuff we do.
So yeah, as a avid math and physics podcast listener, you may be noticing that every single episode that we've put out so far was somewhat planned. We had things, well, not necessarily planned, but we knew what we were going to talk about, and we had like mental notes about points that we wanted to discuss and, you know, things like that. But this episode is going to be more like, I feel like a lot of other podcasts out there where they just kind of sit down and talk, and, you know, I know things that I want to say that are going to be interesting. So it's not going to be like a boring podcast, but it's just going to be about anything physics and math.
Yeah, so there's no defined structure, but it's just going to be all around interesting.
Which I think is good. It keeps the listener on their toes.
Yeah, I mean, I think it's good. I definitely do. Yeah. Let's see.
Yeah, I think I'm going to like this. And also, we're also going to do this more often, I think.
Hopefully.
If it goes well, I think it's...
If it goes well.
I mean, why wouldn't it?
Yeah.
But you know what I mean?
Mm-hmm.
So yeah, before we even start, we do have news as always.
As always.
So first of all, we are at 268,000 downloads.
Wow.
Thank you to everybody who's been listening to the podcast. Also, one thing that I had to mention is that because we posted on Tuesday, we always get more downloads the day we post, obviously. And on Tuesday, we actually beat our record of most downloads in a day.
Oh.
And it was 1,688 downloads in one day.
That's impressive.
Which is
1,600 people downloaded our episodes.
Yeah.
That's wow.
Which is almost, well, not really almost, but kind of there to almost 100 downloads per hour for the entire 24 hours. Almost.
That's crazy. That would be nuts. That would be nuts.
Yeah, that would
Close.
be nuts.
I mean, yeah, not exactly.
more than one per minute. Every minute that goes by.
Mm-hmm. Also,
Yeah.
like we do release like after a certain time, and this only calculates not the whole 24 hours.
I mean, yeah, whatever.
So there's also that. Anyways, but yeah, there's a little bit of that. So if we had released earlier in the day, our downloads will definitely go up. But
that is true.
you know what I mean? So that also depends. But anyways, those are those are news. I think we have more news.
What's like? I'm not done.
Oh, yeah, of course. Of course. That's what I'm saying. We have more news.
Spotify.
Yes,
Spotify. 16,222 followers.
Wow.
What?
Wow.
We
That's crazy.
gained 500 followers this week. Take that in. Yesterday alone, we got 100 followers in a day. Crazy numbers. So keep following us.
Keep following on Spotify or really wherever you listen.
That's the message.
We always like to share Spotify, but I mean, all of them are still equally important. Like we have Google Podcasts too, I believe. Is that?
Yes.
What's Google at?
Google Podcasts, 2,800.
2,800?
YouTube,
Wow, that's nice.
1,900.
19. We're so close to 2,000 on YouTube. I think that would be really cool. I mean, every milestone is a milestone. So, I mean, thank you to everyone who continues to follow, listen, subscribe. And if you're listening right now, wherever you are listening, go happen to follow the podcast. If you're on YouTube, why not smash that like button
Oh my.
and comment on the video. Now, you must be wondering, why would I comment on this podcast?
What would I even say?
What would I even say? Well, I can't tell you that, but I can tell you why you should say it. And the reason is the comment of the week. The comment of the week for this week, we had from last week's episode, beautiful comment from Eric from Germany. Eric states, "Hey guys, I just found your podcast via Spotify a month ago and just landed on the YouTube video." So cool stuff, Eric. "I'm really enjoying the progress you both made through the last semesters. Enjoy bringing up new details concerning about the history of physics, math that have been new to me. And greetings from Germany." So thank you, Eric, for that nice comment. Greetings. Lovely to hear that we have a German listener. We have German listeners.
Hello.
Okay,
I know that.
no.
I'm a cultured man. What can I say?
What I do want to mention, though, is a really cool comment that I read that I came across in the last week's episode that was actually like someone commented that this was a tweet from someone else or like a quote from someone else. And I just really love this quote. So I just really wanted to share it. "If you are not a scientist and you disagree with scientists about science, it's actually not a disagreement. You're just wrong. Science is not truth. Science is finding the truth. When science changes its opinion, it didn't really lie to you. It simply learned more." How beautiful is that?
Wow.
How beautiful is that?
It is.
So I mean, this has a lot of kind of, things to do with also like what's happening right now. Like everyone in their right mind is a neuroscientist now. Everyone can determine.
What do you mean neuroscientist?
No, sorry, not neuroscientist, but like an immunologist. You know what I mean. You know what I'm trying to say. Sorry, but yeah. So I mean, there's kind of a play on that, as well as as the simple fact that at the end of the day, scientists can argue with scientists because like that's the whole job of science. To continue finding the truth. I can prove you wrong in something if I have scientific reasoning to do that. But me just saying something, hey, you're wrong. I disagree with you. Why? Because I do. Like that's not an argument. You're just wrong. That's basically the point of this. And I really like this quote. So thank you, Ghostly Jet, for leaving that quote. Shout out to another comment.
Incredible.
So yeah, definitely a cool quote to read.
Make sure to leave a comment if you want to be next week's comment of the week underneath this video.
Super simple.
Yeah. So now let's get into it. So first things first. During this week, or actually, wait, let me go back even further. I always go back. Coming into first year at university, we had a lab course. And in this physics lab, well, it wasn't a course, actually. It was just our tutorial.
It was part of our lab, part of our physics course.
Yeah, so we took just foundational physics, and the lab course was the tutorial for that course. And I show up to that class, and we have to do Python, which I had no idea. I had no idea what Python was. I had no idea how to code. I've never coded before. And they're just like, yeah, just do this. And I had to just teach myself, basically. Fast forward to second year, where I realized that coding is actually going to be important. Well, I kind of took it a little bit seriously in first year, but not really. Second year, we started doing more coding in astronomy. We had computational assignments, which were all done on Python.
Yeah, okay, but those were we can definitely talk about how ridiculous those astronomy assignments were.
We can. But also, our final project was a Python project where we were given data sets of like binary stars, and then given the brightness at a certain time, you could determine the mass and the period and all that stuff. Anyways, it was a really cool lab. I thought it was pretty cool. Produced some nice graphs.
The most powerful part about now this is like to anyone who hasn't coded before, like this would like who is maybe getting into programming or has thought about getting into programming. The biggest, most advantageous part about programming is that at the end of the day, the whole point of a computer is just to do like rough work.
It's to do the easy things faster.
Exactly.
So
it's just to do like the grunt work just fast.
Like imagine if you had like 1 million toddlers and you taught each toddler how to add 1 + 1, and then you just like send it down the line, and then at the end of the line they would give you an answer, but instead of toddlers it's bits and whatever. I mean,
the whole purpose, the whole premise of computers, like how, like the word computer. Remember when we had the Alan Turing episode?
Compute
the whole
things.
Word term computer came from, well, I mean, obviously this is gender, whatever, but like back in the day, it was women that literally sat and computed, was the whole computer. So taking that to even today, you can actually see what it's doing is exactly that.
Yeah.
And Python is, I mean, all programming languages really are super useful when you have any amounts of data that you want to analyze, right? And that's where I think programming, especially when it comes to physics, again, all of the stuff that we're gonna be talking about with relating to programming is strictly related to, I think, like physics and math and data analysis, because there's a whole programming coding part of it, where you actually program a program. Like you actually create a program that does certain things to a certain to a user, for example, like a user program interface. But in a lot of these things that we're doing, we've been given a data, and we've been given data, and we need to analyze the data. And
the crazy part about Python is that the scientific libraries are so good.
That is the reason why Python is so goated. The reason why Python is so much better than almost every other programming language when it comes to science, especially physics, I would say science though, to generalize it, is because of the libraries. Python has so many libraries. SciPy, Astro, NumPy, like so many libraries.
Realistically though, you only need like 4.
For what?
No, what I'm saying is that
we have still a limited amount of things that we're doing right now,
Okay, what I'm saying is that in terms of, maybe 5. In terms of what we're doing, we need, PyPlot, like Matplotlib, NumPy, SciPy, Pandas, and AstroPy. That's it.
Oh, you learned Pandas in your class?
Well, last year in astronomy, we did the bins.
Oh, that's
Remember
nothing.
that?
No, you're going to actually, I don't actually know how they might go deep into it.
I don't know.
Anyways. So, again, with all of these advantages, so library, again, are we trying to explain coding here?
I mean,
maybe not that fundamental. Maybe not that fundamental, but like, well, again, libraries just help you. Well, they're just classes of objects that are just doing things for you. And I mean, the coolest thing about we can definitely go into a whole programming episode, but that's not what this is going to become. But what I was trying to say is like the big thing about all of these is that at the end of the day, you can program your own code and you can then apply it to, for example, let's say you want to find some property of some measurement in your data, then you would need to parse through all of your data and figure out which one satisfies your property. And especially when you, let's say, have 100 measurements of, I don't know, like some star pulsating, for example, you're not going to be looking through each measurement, right? So, I mean, that's obviously a very simple, vague example, but that's just where programming can be OP. Like, it's just meant, especially in science, to take data, to break it up for you, and to just make your data easy to access, easy to manipulate.
It's not even just that. It's also how so easy it is to extract like visual information and like statistical information about your data set. It's so easy. You can plot your data in 3 lines. Figure, plot, show.
You don't even need to do figure.
Not even.
You can even just plot.
Plot, show. That's all you need.
You don't even need to do show, bro. You can just plot.
I guess.
Plot. You can just...
But in well, not if you're doing like what's it called? If you're doing like a Python, actual Python.
Oh yeah,
script,
no. Then obviously, so that's different. Okay, that's also where it becomes. So a lot of what we've been doing right now in Python is a Python notebook,
which I love, by the way. I love the notebook. I know
because it's easy.
But why do I need to know?
Because a Python notebook, for those that may or may not be familiar with Python, is basically a console. Like it's an inline console where you can run multiple lines. I mean, it's basically a console, but it's not a script, which I don't really like about it, but it's useful because it's
useful because it's easy because you can run cells and it gets stored in the kernel.
Yeah, so it's the console. It's in the console.
Yeah, it gets stored, and you can basically, as soon as you run one, you can go back and forth between them and run them individually, so you don't have to I want to say compile, but that's LaTeX.
Yeah.
You want to rerun everything at the same time. You could just do individual cells.
I mean, you are compiling your code, though, at the end of the day. That is what.
No, when you're doing one
No,
One
but
cell?
even when you click enter,
Oh, yeah,
like
I guess,
compile
yeah.
is technically
Yeah, sure.
what is the
Sure.
process of understanding
Sure.
the code.
Wait, we've gone off topic because wait,
What's top? There's no topic.
No,
That's the whole point of it.
because I started this whole thing by saying that we were doing coding in astronomy.
Astronomy.
Nowadays, like coding is now in my dedicated lab course for physics, my dedicated lab course for astronomy, which is full year, and then also in what's it called? My classical mechanics course. So like 4 out of 10 of my classes use Python. Which is a good amount.
This is
you
for
know what
any.
I mean?
No. I mean, like, we're talking about Python relative to us, but this is like for any physics student. They're going to be using Python.
No, yeah.
Like
100%.
any physics student in any university is
100%.
probably most likely going to be
that's
using Python.
actually no, that's a good thing. If you're in high school right now and you want to go into physics, start Python.
I mean, okay.
You should.
Wait, did your school have a, you didn't even have a computer science
Actually,
class.
I think we had one, but it
But
wasn't.
that's very rare.
I don't
Like to
think
not
so.
really have a big, because I mean, especially
think
in
so.
my school, the computer science classes were like one of the biggest,
Really?
biggest, influx of kids, because that's the future. Like everyone knew that, so that's why they wanted to hop on
Wow.
it. So in my personal experience, I started with Java, or technically I started with Turing.
Damn,
which is-
I can't imagine a high school computer science class. I feel like that would be
Yeah,
so
bro.
garbage.
No,
Like-
no, not at all. Bro, I've learned more coding in high school than I have here.
Really?
100%. Because again, I'm not in the computer science program. So obviously a computer science,
Okay,
of course,
that
of
makes
course,
sense.
of course that makes sense. I'm saying that with my knowledge, like from high school, I can still apply everything that we're learning right now. Because at the end of the day,
Okay.
see, physics coding is not as much programming as is just logic. A lot of it. A lot of it is just, okay, like you have your data in an array or a 2D array, whatever. You have some array and you need to extrapolate some information from the array.
Yeah.
You need to calculate the max, min, distribution, whatever. You're calculating some things based on the data that you've got, which is basically the fundamental thing that you do in this, right? Which you can see differentiating between all of these.
Quick parenthesis right now. NumPy arrays are so insane. The things like compared to a regular list, they're so crazy. If you think about it, like just the dot reshape.
There are a lot of methods in, again, this, and the interesting thing about it is all of these you can define all of these yourself too.
Yeah,
Like the dot, the whole
Yeah,
thing
those
of
are
that,
functions.
that all comes from just basic understanding of how Python and all these programming languages work, right? Because Python in essence is an object-oriented programming language. You might have heard of that name before, which is basically what means is that every single data, like like when you open up like your console and all the saved values, all those values are basically their own object. Is like a way to think about it. And every object has instances. That means they have things that you can do within the objects and stuff like that. So NumPy is a library, or it's a class that's basically an object. So NumPy dot something is just a function within that object. And we've learned that now, but it's just so, because again, this was all that I learned in like grade 10, grade 11.
But you were doing just Java.
No, so in grade 10, I started with Turing. Now, for any of you listeners that have done Turing, please put it in the comments below, because I want to talk to you. Because Turing is the most
Turing?
garbage language in the world. So it's based off of like, it's basically like really fundamental code.
Okay.
Like really just ABCs. Like, nothing technical, nothing.
Is it like a browser?
It's very, very basic, and it's not fun at all, but it's something that I went through to understand basic level coding. Anyways, that's not the big part. The big part was grade 11 and 12 where I did Java.
You did coding before grade 11?
Yeah, grade 10 comp sci.
What?
Yeah, bro. It's crazy that
What?
you don't even know.
No, that's not a thing.
Yeah,
that's
man.
not a thing in my school.
Grade 10 comp sci was a thing.
No way.
I still remember my teacher.
That's
I loved him. Yeah.
Because it's not recognized by like universities.
What?
Like computer science programs will never ask you to have computer science from high school.
Really?
Yeah.
No. I know that, of
They'll-
course.
they'll
But
never do
again,
that.
there's no point. But see, the thing is, if you're not versed
But
in
that's-
any programming language,
You can
and you're
still-
going into you're gonna be railed. Are you crazy? There's no, okay, no, not in that. What I meant was it's going to be hard.
No, obviously.
Like, it's going to be really hard. Because
Okay,
you don't know.
okay, but think about Ray. If you're going into computer science,
Yeah.
you like it's for a reason.
Yeah, but
know
you
what
have to
I mean?
understand today, like the level of people that get into these programs. Like, I have a lot of friends in CS. You know this.
Yeah.
They're all goated. Like, you
No,
get
yeah.
into it by knowing programming languages.
Yeah.
Almost nobody
And
in the computer science program did not know a language.
Yeah,
before
the thing
coming in.
about computer science is that it's so sick that like every single person in your class is like really smart, but everybody does things differently. You know what I mean?
That's the beauty.
That is the beauty
That's the
because
beauty.
because everybody's so smart, but
Yeah.
they all have their own way of thinking, so that when they approach a problem, it's like they do it very effectively, but you'll read their code and be like, "Wow, I'd never
because
never, ever."
and that's the beauty of programming, because that's why in my opinion, and like, just hear me out real quick, like computer science in the fundamentals is like as hard, like fundamentals as in like really getting to know what is happening in there is basically like rigorous math.
Yeah. Have you ever watched the interviews, the Google interviews, the coding interviews? You've never watched those? No, you have to. Okay, so it's like an interview where a recruiter for Google interviews somebody, and it's like recorded. Like they both have like face cameras
shit.
and screen recordings of what they're doing, and the interviewer just asks them a question. And for example, one of them, it's like, okay, you have a list of airports and you need to like only some airports are connected directly. And
Oh, we literally had this problem.
yeah, like
in my class.
given or whatever, you
Okay,
need
sure.
to,
Yeah, I get what you're saying.
and then the interviewee has to like write
Code
down
it,
it,
yeah.
but like write it down in like
Never heard
in
of
like a
this.
Google Docs, so like he can't check if it's right.
Oh no, that makes sense. No, that definitely makes sense. That
and
definitely makes
he
sense.
also like he can also draw things to be like, okay, so here's how I'm thinking about this. You want to do this and do this,
Man,
and then like
if you see computer science contests, bro, like
yeah.
literally basic. It's almost like, you know, you can compare a computer science contest to a math Olympiad.
Probably.
Because a math Olympiad, if you think about it, is basic questions. Literally, like you have 5 apples and 6 bananas kind of questions. Is literally how it's framed.
Olympiad?
Yes.
No.
The questions are all rooted in base
Okay,
logic.
they're easy, but not.
No. I never said they're
like-
easy. No. They're not
No,
easy.
no, I
That's-
didn't. No, I didn't mean easy. I meant like they're short questions, but they're still like
No, but I still believe
the hardest
they're-
possible questions you could
but
ask.
they're put in such an easy way, is what I'm trying to
Yeah.
say, right? Like in these Olympiads, they're put in such an easy way that you can just, okay, it's so simple. You try to do it, you have no idea what to do. In computer science and like all of these computer science contests, like I've seen, like my friend. I mean, I actually also took place in some, but my friend's really, really, really good, and he actually has won a few of these, and all of them have such. Like some of them are complicated technically speaking but it's so easy to understand for a computer scientist. Like even the words are super simple to go through. What the problem is asking, you get, but how to actually do it
Yeah.
is so crazy, because if you look at any of these computer science exams, you're basically given something to do and you have to program it.
I've never done a computer science course.
Oh, well, yes, of
never
course. Then how would you?
seen
Yes,
it.
of course. No. I'm not talking about an exam like a school exam. Sorry, I'm talking about like an Olympiad, like an Olympiad. You know, like a competition, like a CS competition. So for those, I mean, there's also a really famous YouTuber actually that gets like first place in a lot of these things, and he codes, bro. He codes faster than you can think.
Damn.
Like, I'm not even joking. Like, this guy sees the question, he's like,
Oh
I'm
my
like,
God.
how are you even thinking? Anyways, so the point I'm trying to get at is that all of these people, like the Olympiad people and these guys, have something very much in common, which is this way of thinking in logic based, like, you know, rigor. That because coding is fundamental in logic. And that's why it's so powerful for physics. And if you like math, if you like stuff that we've been talking about, in math and proof-based math,
Yeah, CS
logic,
is
like
so
CS
fun.
is amazing
So
because
fun.
the feeling you get when you prove something is the exact same feeling you get when you finally figure out a function in coding.
Yeah, no,
is the
that's true.
exact same feeling.
That's true.
That feeling of I finally or something like that.
But coding is I think it's
It's more annoying.
it's-
It's a lot of that's very annoying.
no,
though.
it's annoying,
It's
but
very annoying.
but it's in some way I think it's kind of easier because you get an instant, like somebody tells you you're wrong, and that's when you have a bug.
100%. But let me tell you why you might also think it's easier, and that might be Python, because
Oh yeah, I
Python,
guess.
I think the whole purpose of it was to be like super super simple. Like if you ever read
Why
Python,
would you want something that's complicated?
because it's not no. It's not about the level of complication. It's about how much you're telling the program to do versus how much the program is doing for you.
But isn't simple better?
No, but you have to understand
Doesn't everybody
the
want
people. No, because a lot of times you want to tell the program to do very explicit things in very explicit ways. But sometimes Python takes care of things for you. For example, the easiest example that I can give you is errors, catch errors. It almost never gives you an error. Like there's so many times when like you'll make like a fundamental mistake, like you'll change like a variable up top and something like that, and it'll still run. How did it run? It's like small things like that.
I don't think that's ever.
No, that actually does happen because Python understands the error. A lot of time, even with indices, when you mess up an index,
No way.
Python will figure out.
No,
yeah,
that's
so many
not
times.
true. I've never seen that ever. I've gotten so many like
You'll
index
get list error,
out of
you'll get your
range.
index out of bounds.
Yeah.
But what I'm trying to say is there are many instances where Python will understand the error and not explicitly when you just write it down like that.
That is kinda
But
bad.
believe me when I'm saying like when there are like more complicated things to do, you definitely see a little bit lack of Python. Because again, Python is supposed to be just that very bare bone basic coding language. Like even the actual codes it's not codes, man. It's English. It's print. It's it's
guess.
read.csv, stuff like that.
I guess.
You
but
know what I
that's-
mean?
That's a good
So
thing. Why would you not
I'm not
want
saying
that?
it's not. I'm saying it's different.
Why
from
didn't they
everything
do that the
else.
first time around with
I'm
every
saying
other,
it's
with every other?
different with everything else because everything else also was made a lot before. Python was also, I think, relatively.
No, it
newer.
is. It
Yeah,
is.
that's what I'm saying.
But-
so like C and everything is like your foundational. Like if you look at C, it's literally like the computer is not doing anything. You're basically telling the computer exactly what to do. It's just that you doing it yourself will take a lot more time is the point of it.
Yeah.
Right? Which is why the computer is there in the first place, just to speed that process up. And which is why programming was invented in the first place, just to speed up that process of having a computer in the first place. Right? Because the original computer was what? The console. And at the end of the day, you were just entering lines here and there and just getting values. You could access the internet through certain things and stuff like that, through a telephone back in the day and everything. But at the end of the day, programming is just so rooted into computers, into what we have today, that just understanding the way that programmers think is a really nice way to get along, especially in physics.
Did you know my dad? I'm pretty sure, if I'm remembering this correctly, because my dad worked at the University of New Brunswick after he graduated.
Okay. Did you graduate from there?
Yeah,
Oh.
in computers.
Oh, really?
Yeah, like hardware.
Wait, I know this. You
Yeah,
mentioned
yeah.
this before. You mentioned this
like
before.
hardware computer
Yeah.
science or something like that. And after he worked at the university, and I'm pretty sure he installed like the very first, or like he helped install the very first like internet connection in Canada, like North America. It was an IBM machine
What?
at the University of New Brunswick.
That's nuts.
Yeah. Crazy.
Oh,
like something
my.
like it's something like that. This was like in the,
long time.
the 80s or 90s or I don't know. You know.
Internet probably 90s. Oh no, no, that's the world. Internet probably earlier. Oh, I don't know.
Like it was probably late 80s.
Yeah.
You know?
Yeah.
Yeah.
That's crazy.
Yeah, no, yeah.
That's really nuts.
Yeah.
Because firsthand, has he told you anything like stories about it?
Yeah, he
Like
has.
just spoken about like
No, he has,
how he
yeah.
did it?
Well,
Already? I mean, I'm
as if I
assuming-
would understand
yeah,
that.
as if he would've. No, because even computer engineering is its own thing.
Yeah.
Right? Like, and even that itself has so much programming to do with it. Because And this is where also like you can extend programming into any level of, and here's where programming becomes really broken. And here's where you need it. Simulation. Oh, I was very close to the mic, but simulation. Simulations are the key to higher level physics. Like in real life, there are only so many things you can do.
Oh, you know what's an amazing segue right now? Is
Literally in the middle of talking
no,
about
but
simulation.
it has to do with
Okay,
simulations.
okay.
Because, simulations, yes, no, you're right. Obviously, the key to upper level.
Crazy.
Or some topics. Not,
Okay,
not
no, what I'm
everything.
trying to say is if you can get a system that you are trying to analyze, and if you are able to simulate that
Yeah.
system, the amount of things you can do is crazy.
And the first thing I thought about was like the Navier Stokes equations
Okay.
that you have to simulate because you can't
You
like
can't.
some initial conditions whatever.
Literally.
But
Blow
the
up to
Navier Stokes
infinity.
equations are differential equations.
Mm-hmm.
And one thing that's actually crazy if you think about it is that like a general differential equation, so some function of x, y of x, y prime of x, and ... equals to 0, for example, or some, whatever,
Whatever.
does not have a solution. Or we don't know how to find, like it has a solution, we don't know how to find it. Or we don't even know that there is a solution.
And this is, again, we were able to do this through the simulation.
Yeah. But the thing is, with simulations and all that stuff, you can find, like you can graph solutions, but it's not following any equation. Like it didn't solve the equation. It just uses the fact that it knows how the rate of change behaves with respect to the other derivatives and all that. And then they just update the time step, right? And then they keep plotting along. Like they don't know what the actual solution is.
Because because that's exactly how you would simulate anything. The time step is a very fundamental thing in all physics simulations.
Yeah.
And in all physics simulations, the commonality is a physics engine. And with a physics engine, you can basically do whatever you want. Physics engine is just a way of basically saying, hey, you have this data or you have this world, apply physics. Is basically a way of saying add G, add air resistance. So for example, and I actually have a mate that didn't. Mate. Man, I've never said that. Oh, wow. I have a friend that did this in grade 12 computer science that for one of his programs, he simulated like some complicated ball moving on Earth with like a very realistic physics engine. And what he was able to do basically is he obviously knew the parameters of the object because he's the one that coded it in the first place. So he can play around with the parameters, of course. You can play around with the air friction because they're just vectors. Literally, like if you really understand like the fundamentals of like a physics engine or really about any programming, you're like, oh wow, that's just so simple. Like there's so many things nowadays that I look at and I'm like, oh, how do you think the guy programmed that? Like I look at a game that's like some of my friends I'm playing, I'm like, oh, how do you think like that button, like why does it jump you there instead of there? So many times. And that's all based on how you define this, which is why understanding this Python, understanding code understanding simulation is so key, And I mean, where programming can help too. I mean, clearly moving on to continuing to the differential equation part of it, like simulating the Stokes equations is because after the simulation, we got the fact that it either doesn't or must, right?
No, we already knew that.
No, because the math didn't exist though. But weren't we like more certain about something after the simulation?
No, we knew basically the simulations are just to show real world examples. Okay, for example, if you have like water bending a corner,
Yeah, I remember
the
this.
velocity goes to infinity, right?
Yeah.
But it doesn't actually. So mathematically, we can't figure out what's wrong with it. But if you simulate it, then you can just see what happens. And you just, it ignores the, well, it doesn't ignore it.
Simulating turbulence is like one of the hardest things to do.
Yeah.
Like we have not been able to do that right now.
Yeah. And from what I said earlier, like F equals MA, classic.
Yo,
Grade
I mean,
10.
Yeah.
What?
No, I mean, I was just talking because if you wanted to segue, because we were talking about differential equations.
No, yeah.
Just just like the whole prospect of differential equations. And well, in this case, you are simulating them, and it's super simple to do that with a program.
Yeah.
Right? Because there's so many complicated systems that you can get that you have no idea how to solve, or you don't even know what it could look like. But one piece of code, and it'll just plot it for you. Like Mathematica, which I believe there's a matplot thing for it, can just literally just plot curves for you, man. Like, it's super simple. Like, you give it a differential equation, it'll give you the whole spiel.
I've done the class.
Mathematica?
No, I've done.
No. I'm talking about Mathematica.
I know, I've used like.
Oh, you've used Mathematica. Oh, no, because Mathematica, they don't.
Other
Yeah, because
things.
Mathematica, for anyone that. So Wolfram Mathematica, it's super expensive. I shouldn't be saying this, but it's very expensive.
What?
It's very expensive. Point that I was trying to make is that Mathematica is a program that commonly simulates a lot of these things. You know, that basically you give it some stuff, you give it some numbers, and it simulates stuff, right? Common example. Again, just continuing on to where you can see the use of coding, especially with examples in differential equations, right? Like the heat equation, for like any equation that contains, well, the derivative, really, I mean, a differential. And if you want to see what would happen over time, stuff like that, like there's so many ways that simulations can help.
Okay, but you completely did not let me talk, because
Why?
here's what I was gonna say.
Oh.
F equals ma is a differential equation. And relating to what I said earlier, is that it's equal to mass acceleration. Acceleration is the second derivative with respect to position, of the position with respect to time. And force can be a function of time, position, and velocity. And like nothing else, right? Because it's a function of acceleration, but it's literally equal to a constant times acceleration. So, you know, if the force is a function of time, position, and velocity, there is no general solution, which is why like classical mechanics problems can get so hard using Newtonian mechanics. So what they do is they teach us ways to solve this differential equation for specific cases. Like,
Okay.
for example, you have force as a function of position only, right? So in that case, if your force is a function of position, on the other side, you have mass times the second derivative of position, and then it's just separation of variables, because then dt f of x, and then integrate on both sides. That has a general solution. If force is just a function of time, same thing. You have a function of time, and on the other side you have d squared x over dt squared. You just integrate twice, separate and integrate twice.
Similar.
If it's a function of velocity, though, it's a little bit different, but not really, because all you do is you use chain rule.
So here you're saying they're individual, not velocity and.
Yeah.
Okay.
Yeah. If it's, and these are applicable to like pretty much everything. Well, pretty much every to a lot
so
of
how
things.
how does a general solution get solved now that you have?
There is no general solution
So then where does this help you? Just in finding
for specific problems.
Oh, for specific problems. So
Yeah.
if it's this, if it's this, if it's
Yeah,
this.
like for example, if you drop a ball, or if you're doing anything with air resistance, the force is a function of just velocity, because air resistance is
that
just a
makes sense.
function
So
of
those
velocity.
are the hard ones.
Well, no, those are easy ones.
I thought the
it's just
position
velocity.
and the position and the time were the easy ones.
No, the velocity is also easy.
Oh,
No, I meant the hard ones are when it's time, position, and velocity.
oh yeah, okay. When
Those
it's
are
all
hard
of them.
ones.
When
Yeah,
it's
yeah.
all of them.
But no,
Okay.
velocity has an easy one too. It's something like, okay, dv by dx times dx by dt, the just chain rule, right? That's equal to dv dt, which is a. Am I speaking too fast right now?
No, I think that's
Okay.
fine.
So then you have dv dx times dx dt. dx dt is velocity.
Yeah.
Okay. And now you can just separate your variables.
Valid.
because then you have a function of v.
Oh yeah.
And then you put
Velocities.
t on the
yeah,
other
so
side.
then that wasn't the hard one. Okay, so
Yeah.
the hard one was when they're all together.
Yeah.
Wait,
Yeah,
so
well,
do you
when
have a
the-
way to
wh-
do that,
wh-
or is there?
No, there's no way.
Sheesh.
There's no way. It's what I said earlier. If you have a general differential equation that's just like some weird non-linear whatever of derivatives and the independent variable all together, like there's no, like if I tell you, okay, what's the solution of natural log of x divided by, like you could literally do anything. There's no general way to solve it. You only know when to solve it when it follows specific rules.
No, but general way to solve it versus general solution. I'm saying there's a general solution
to the ones you know how to solve. I'm saying all of the other ones, we have no idea how to solve them. Like the only
we have
thing,
no idea as in like we or like
no,
we
everybody,
as in like mathematics.
everybody, mathematics.
Damn.
Ray, think about it. They're in the class you're doing right now. What do? They say, if your equation looks like this, here's how you solve it.
Because we are being told like ways to solve.
Okay.
Because we're young.
Okay,
obviously,
no,
we're
no,
not
no.
into that.
But
I'm
why?
saying, is there? So there are. I mean, it makes sense that there are things that don't have a solution.
Like, why do you think they tell you, oh, exact equations have this form, and here's how you solve it? Why? It's because if it was a tiny bit different, we have no idea how to solve it. But on the off chance that your equation looks exactly like this, we know how to solve it.
Nah, bro, Wolfram knows how to solve it, man. Believe me.
I mean,
That's what I'm saying.
not all the time.
No, of course. I'm saying if there are differential equations that don't have solutions, that's different. But I'm saying differential equations that we don't know how to solve.
No, every differential equation
That has a solution we know how to solve? That's not.
No,
No, right.
every differential equation has. Wait, how do I say this? Okay, there are differential equations, I think, that math, doesn't know if it has or doesn't have a solution. Like, it just doesn't know. Because think about how crazy you can make an equation that has n derivatives, and you just make it insane. You have no idea if it has a solution or not.
No, but just because, that's what I'm trying to say, just because you don't know it exists doesn't mean it doesn't.
But I think it's like a rational versus irrational number kind of deal. Like, there are a lot of rational numbers, but there are a lot more irrational numbers.
But that doesn't mean that they're not. So you're saying that there are, again, I'm not actually sure about this because
I think so.
I'm just learning differential equations right now. But are you saying that there are like multiple differential equations that we don't have a solution to? Sorry. No, we don't have a solution to. That a solution doesn't exist. I'm not saying we don't know the solution. I'm saying
Like,
it
for
doesn't
example,
exist. Those are two different things.
here's an example.
Let's hear it.
It's okay. It's not that it doesn't exist. It's like you'd have to define it to exist. Here's an example. Do you know the Lambert W function?
Explain.
So the Lambert W function is the inverse of x times e to the x. So
Okay.
for example, the natural log is the inverse of e to the x. Lambert W function is the inverse of just x times e to the x.
Valid.
Which means that if you plug in, for example, pi times e to the pi into that function, it would give you pi. Okay. That is a function that was like invented. You know what I mean?
Okay.
And it is the solution to some differential equations. What I'm saying is that there are differential equations whose solutions haven't been like defined yet. And like we wouldn't know how to like write them down.
There's no way Mathematica or something or a software though won't be able to calculate this.
I mean, Ray, Mathematica
Do you
Mathematica can give you the Lambert
wait,
W
do you
function as a
think-
let
do
me
you
finish. It can give you the Lambert W function as a solution to a differential equation or a component of it. But imagine if it wasn't programmed into Mathematica because we didn't
No, but
know
that's what I'm
about
trying to
it.
say. I don't exactly know how Mathematica has been programmed because I don't think it does it using like, again, could be completely off on this, but the way that I would make a program, if I'm trying to make a program for anything mathematical, well, would be to do it the hard way in the program. Because the whole point of a program is that it can do it the hard way. So if there's like a rigorous
What do you mean the hard way?
Again, I'm not too well versed in differential equations to really know how to solve an equation that we don't have a general idea to solve for. But there's no way that Mathematica only uses what we already... Okay, I shouldn't say no way, because again, I don't know how it's programmed. But I don't think, at least, that it's only based on how we know how to solve differential equations. There's probably something that it does that we simply can't do because it has a program. Like, think about this.
I don't
think about
think
it.
so.
I mean, think about it as simple as this, though. Like, if you have x from 0 to 2, there are infinitely many things in there. You can't do it by hand. The program can. Like, just
What do
an
you
example
mean?
as simple as that. An example as simple as that.
It can do an infinite amount of tasks.
Well, it
is
can,
what
no, not
you're
infinite
saying.
amount of tasks. I'm saying it can iterate through.
Infinite value.
Okay. Infinite
Okay.
is, okay, what
No,
I'm trying to say
there
is a
you
lot
go.
of data.
Okay, a
What
lot
I'm trying to say
of.
is a lot. Again,
A
okay,
lot
sorry. Not okay. Using the infinite term was the incorrect thing. But it's what I'm trying to say is it uses a lot of data. So given a very, very complicated differential equation, we might not know how to solve it. But again, I do doubt that a software wouldn't also be able to solve it. Because that would be crazy.
No, I
You don't think your
Absolutely not.
software can solve like your differential? Like, obviously, like there are equations that can't be solved, like the Navier-Stokes equations, for example. Like, solve that, you'll get $1 million. But all the other ones that have like really complicated ones, I'm pretty sure Mathematica can still solve.
So it has been confirmed not all differential equations will have solutions.
Okay, well then that breaks the whole thing. Okay,
There you go.
Okay, well, shit. Okay, so that's a thing. That's a thing then. Okay.
Yeah, haven't you seen the existence and uniqueness
Of course.
theorem?
No, I know that.
Existence.
No,
That's
I
what
know
it means.
that is true, though. I know that there is a way. I mean, it's very simple. Simply, if the dependent functions are not continuous, then you break the whole existence and uniqueness. Like, I get how it works. I get why a function won't exist. But I'm saying if you know it exists, like from the theorem, you know it exists, and this is what I'm trying to say. And you know it exists, but you don't have the tools to solve it. Does that, you know what I mean?
Oh, well, no, you leave it up to a computer if it's possible. I'm saying sometimes it's
Was
not
that not my whole
possible.
point this whole time, though?
No, what you were saying was that any differential equation you can throw it into a computer.
Originally, I did believe that. No, because I was asking you, does every differential equation
No,
have a
and
solution?
I said
That's what I'm
no.
saying. Oh, did you?
I said no. I said I even gave the rational irrational comparison.
No, irrational. I would have immediately got, because I know the existence and uniqueness theorem. Like, I understand the uniqueness
No,
theorem.
I said the equations are. This is not fact. I'm saying I feel like the differential equations that have solutions are like rational numbers, and those who don't have solutions are like irrational numbers. Like you can write so many more differential equations that just don't have solutions than do have solutions.
Well, yeah, that's just from like basic. Yeah, it's the same way you prove the irrational rational. You can just go like a way of thinking, at least. I understand that level of thought. I understand that level of thought.
For sure.
Okay, I mean, no, that definitely does make sense. Because originally I wasn't quite... No, but I definitely knew the uniqueness. That I wasn't just thinking of that. Because I was definitely thinking of maybe specializing, or maybe not, I didn't specifically say it, was looking at, things that at least have a solution. We just don't know how to solve it yet. Because I would think that the program would be able to do everything. Because like that's the whole point of all the programming stuff we've been telling them to learn. Imagine they learn all programming. They're like, what do I do with it?
You know what's funny, actually?
Definitely learn.
You know what's funny? Today, I actually, while I was doing classical mechanics, I read this was about damped and driven oscillation.
Oh.
So it's like periodic, right?
Yeah.
And they basically gave, like, they didn't prove it, but they just showed how you can essentially give a solution for the coefficients as a Fourier transform of the function that you're okay.
You're gonna have to repeat this whole thing.
Yeah.
Sorry, I wasn't even
Okay,
knowing that this was gonna come up.
So take this.
Okay, let's
You
hear it.
you have an oscillation, and you have a force that's driving that oscillation. Now that force has to be periodic, but it can look like anything. It can be a square wave. It can be a triangle wave. It could literally...
Yeah, because it pushes away from equilibrium, comes back. Pushes away from equilibrium like that.
It could do anything. It just has to be periodic.
Okay, valid.
That's it.
So these are the 2 requirements.
Okay?
Okay.
And so what the textbook showed is that, okay, let's say you just have a cosine wave as your driving force. It just goes up and down. Boom. You can solve for a particular solution. And what you do, obviously, if you've ever taken an ODE class, you guess the solution.
That's such a classic. That's such a classic.
You guess the solution to be some constant times e to the I omega t with just the same omega as the driving force.
Okay.
And, okay, here's a spoiler. It works. You can solve for this, and you get a particular solution for that oscillation, and it has the form of some constant times e to the I. Well, it's the
which is sine plus cosine,
it's
which
the
then is your
it's
Fourier.
the real part.
Yeah.
The real part of
I get it.
that. Okay, but the coefficient has an imaginary part, which means that
Wait, but wouldn't you just break this up into your cosine
you
sine,
would.
which is your Fourier,
no,
or is that not?
you would.
Yeah.
But here's the thing. What was I saying? The coefficient of the e to the I omega t has an imaginary part, which means that when you take the real part, you do get the solution for the position as a function of time. But now, what if your driving force was, cosine omega 1 plus cosine omega 2, and it's just a superposition? As you learn, ODEs are like linear ODEs. You can just add particular solutions. And so you'd be adding e to the I 1 omega t times some constant, take the real part of that, and then plus the real part of e to the I omega 2. Okay? But from Fourier's theorem, whatever, or Fourier integral theorem, you can represent any periodic function as the sum of sine and cosine waves, which
Which is your
cosine waves are the same as sine waves, but offset, right? Yeah. And so instead of your driving force being just cosine, it's just an infinite sum of cosine waves. And so your solution is now an infinite sum of a times e to the I, some omega value.
Real part.
Yeah, well, you take the real part. Yeah. But now it's an infinite sum, which means integral, everybody.
Hey.
You take the integral, and this is just like I was talking about in quantum mechanics. You take the integral, the coefficient becomes a function of omega, right, the frequency, and then you multiply it by e to the I omega of that omega, and then you integrate over all omega values, or the ones that are useful to you. If your thing is a simple cosine wave, well, then you can just guess. Well, you don't have to guess. You can remind yourself that a cosine wave is e to the I omega t minus e to the minus I omega t divided by 2. And so this is, if you're taking the integral, the only, your function is basically a delta function at that. Or since you're doing the imaginary part, it's going to be a delta function at omega and minus omega. And so when you integrate, you get some coefficient, which is 1/2. It turns out to be 1/2 times e to the I omega t, and then minus 1/2, which is that particular coefficient, e to the minus, and then you get your thing. But the whole point of this is that you could take any periodic function, and the solution to the differential equation is going to be the integral over all that stuff.
That's pretty interesting.
Yeah.
So
plus the homogeneous.
So Fourier transforms basically is what you just showed up. You just showed that Fourier transforms very closely linked to any.
Because at the end of the day, it's superposition, right?
But this only exists. Oh yeah, so for an oscillating, with a periodic force.
Yeah, so it's periodic, and this is just simple superposition. The only step that your brain has to take is to go, okay, I'm going from adding 1, 2, 3 cosine waves to infinite cosine waves. That's the only step your brain has to take. And then when you go, okay, finite sum to infinite sum, you take the integral. Boom.
That totally makes sense.
There you
That's
go.
pretty cool.
Yeah.
That's pretty cool.
But it did say, like, after it presented that, it said we're not going to be using any of that. But it's just an example of how, like,
in this
should be
week
thinking.
actually in one of my tutorials, my TA was like, I don't know why. Anyway, my TA was like, in classical mechanics, it's actually a very popular thing to multiply an expression. So it's just harder to do it in the real system. So you multiply an expression, or basically make it imaginary.
Yeah.
Make it imaginary. Do the math with the imaginary. Take the real part.
You don't
No.
multiply
Obviously,
by anything.
It's not. No. It's not exactly like yours, but your example made me think of what this is. So in this case, it is EI.
It is always easier to go imaginary.
No, yeah,
surprisingly.
which was the whole thing that he was saying. It's
Yeah.
like some systems, some expressions can be very complicated, and having the fact that Euler's formula, having all your imaginary exponents, all those laws, using them together can definitely be very helpful. So what a very common practice in classical mechanics, I mean, you're going to learn it. I'm hopefully going to learn it next year. Same thing. Make it imaginary, literally by just multiplying it by an imaginary exponent or a complex exponent. And then at the end of it, after all your math is all well and done, you just take the real part of it. Right? And that just makes it bada bing, bada boom. That's super simple. So yeah, that's a pretty cool way to do it too.
Yeah. Well, thing about classical mechanics that I enjoy. Well, okay, a couple things. So first of all, when you talked about imaginary numbers, surprisingly, well, maybe it's not surprising, but it's always easier to go imaginary. It's always easy. And the thing that always shocks me is how, like, it literally works. Like, imaginary numbers just work for some reason. Like, who would have thought you could just imagine a number exists and it just works in math? When you take the derivative of e to the ix, let's say, it just so happens that the I cancels with the I and makes a negative sign and comes down to the cosine, so that when you take the real part, you get a sine. When you take the imaginary part, you get a cosine, which is exactly what your trig functions do. So, but the thing about using imaginary numbers is that it holds two pieces of information at once. So it's like a vector.
Well, you're talking about a complex number.
Yeah.
Yeah.
I'm saying a complex number holds two things at once. The real and the imaginary, and you can extract whatever you want at any time. Like, you can encode information into the imaginary part and the real part and keep track of it, and then at any point
and that's simply because of the fundamental difference between the real and imaginary. Knowing the fact that they are in fact orthogonal bases, because they don't have wrong exactly. It's not exactly orthogonal to the wrong word, but what I'm trying to say is that they don't have any influence on each other. Like E1 and E2, for example, are no influence on each other at all. In the same way, just like a vector space, you have a real part.
Except when you multiply them.
Oh, except when you multiply them, yeah. But and then even I starts to affect it, of course.
But then that tells. My god!
No, but even when you multiply things, you can still break it up into the real and the thing. Like, even if you have 5i,
but
you'll still have 0 plus 5i.
The craziest thing ever is, okay, what if I tell you, okay, multiply, 5 plus 3i times 3 minus 6i. Like, you can't do that in your head right now. But okay. It would take you at least 30 seconds.
Yeah,
okay?
yeah, of course, yeah.
But if I told you multiply 2 e to the I pi over 3 times 3 e to the I pi over 6.
Light.
You multiply the amplitudes, you add the things. And those numbers represent complex numbers that can be written in terms of real and imaginary part. But working with the exponential is so much easier in every single case.
No, that's where the goated exponential comes in.
Yeah.
Like, we're just right now focusing on the imaginary, but yeah, the exponential itself is a whole new world.
Yeah.
Because that, like, the moment you get an exponential, you get all your exponential laws, you get your ln, you get all your good stuff. Because, I mean, exponential shows up literally everywhere. Right? I mean, and even in what are we talking about? Yeah, so in the exponential case, I forgot my train of thought. because I was trying to say something before that I was thinking, and I had this whole thing, but now you said something and I just forgot.
Here's something interesting.
Shit, never mind.
The natural log of I. What do you think that is?
Wait, what?
Well, I know the answer, but like
1 minute.
the natural log of I
means e to something equals -1. No.
Ye-
Yeah. No, sorry.
Yeah.
E to something equals the square root of -1.
Yeah, but if you just think about it in terms of polar, it's
Oh,
e
in
to
terms
the
of
e to the
polar.
I pi over 2 is equal to I. So when you take the natural log, it's just I pi over 2. So natural log of I is I pi over 2.
Oh, you convert
Yeah.
to polar. That's
Yeah.
smart. No, that's smart.
No,
That's
it's
smart.
just fun problems
Just-
like that that I
that's
really
cool,
like.
That's cool.
Cause
Yeah, I mean, even converting bases like that is so useful. Like polar to
yeah,
even like that can just break, like open up your whole problem into a whole
man,
new
using spherical coordinates, crazy.
thing. I think I would
Crazy.
say something with when I came to imagine. Oh yes, I mean, it's not a big thing, but it's just something really cool. The fact that in every differential equation, if you do happen to have a complex roots or any kind of
You
complex,
just take the real part.
you take the number one, you take the real part. But what was really cool to me too is that the imaginary part is also a solution.
Yeah. No, but that's actually not because. Here's why. Because when you get complex roots, what happens is that the coefficient in front of, like, you'll have like a C1 cosine and then a C2I sine, something like that.
C1 plus C, yeah.
But what you do is you say, okay, well, the cosine is one solution and the sine is the other solution. The actual reason why that's true is because when you're dealing with complex numbers, the constants that you multiply them are also complex.
Yeah.
Which
Yeah,
means
C1,
that
C2 complex.
which means that you can you just work it out on a piece of paper. But if C1 and C2 are complex and you decompose them into their real and imaginary parts, then what you can do is you can literally get the real part of that expression has some other constant times cos and some other constant times sine, and then you'll have an imaginary cos and an imaginary sine. And so you actually do get linearly independent
Literally different,
things,
different
but
things.
they don't explain it to you. They say just take the imaginary part.
No, because again, all of this works because of the fact that these guys don't influence each other, because your real and your imaginary, they don't have any, and which is why you can again use the classical mechanics thing, like just by multiplying an exponent, a complex exponent, it makes the math easier because we have math to do with complex exponents, but the actual problem itself is completely unchanged because again, the complex is not affect, or at least the imaginary, I shouldn't say complex because the real part of the complex does affect the real. But I'm saying just the imaginary is not at all influencing the real part at all. Just
But
helping
it's
the math
still
along
it's
the
still
way.
useful because obviously
Still
if
super
you're
useful.
if you're doing like simple harmonic motion or anything that rotates, the sine can, like in the case where you take a derivative, the sine becomes important because the real part of the derivative is going to be the sine term. If you take two derivatives, the cosine comes back, and so even the imaginary part still stays relevant.
Yeah, so I mean, clearly they're important, and you can just drop. Yeah, like the eye is it's a very cool invention for sure.
They just
can have a whole
They just
episode
made
on
it
eye,
up.
man,
We talked about types of numbers.
Yes, 100%. Yeah,
I don't
that
know
was
if
really
we were that smart though at the time.
I don't know. I think we can definitely go on a more
This was last year.
in-depth explanation on complex numbers.
This is
we can
literally
talk about
a year ago.
Yeah,
More than a year ago.
types of numbers was 30 something.
30?
That's 50 episodes ago. Yeah.
Damn.
No. Yeah, it was 30 something.
Wow.
Yeah, because big math. Yeah, 100%.
That was a year
It was
ago.
30 something. Damn.
Yeah, crazy.
Long time.
Do you think should we listen to it and see if we were stupid?
I mean, that's the whole point of the podcast,
No,
though.
yeah.
I mean, I think all the
No, yeah.
listeners, too, should be like,
Yeah.
should be glad. I
We're
mean,
not-
obviously, but
We're not genii over
we're
here.
absolutely not. We're just two individuals who love science enough to just spend hours talking about it. Because we just are inquisitive to know more. And the fact that we go back to our old video and we're like, oh my, we learned more, means it's been working. Our goal is being reached. Because the whole point of going to next year as well to learn more, to be smarter, to know. Well, smarter is very subjective, but you know what I mean. To learn more, have more knowledge, know what to do in the field and stuff like that, which we're clearly learning. So, yeah.
I guess I hope the podcast is getting better.
I hope so.
Maybe.
I think so.
No,
I think we're definitely a lot more comfortable. I mean, with each other, we've always been comfortable, but in person now, I think this is definitely a little more. Hope you guys like. I think I saw a lot of positive comments, a lot of positive feedback.
we got 100 followers yesterday. That's crazy.
That's crazy. That is crazy. 100 followers in one day.
In a day, yeah.
That
crazy.
is insane.
It's
That's
not the
actually
first
really-
time.
Oh, really?
It's not the first time.
Well, shit.
No, we've actually gone like 120 in a day before. Yeah.
So just Spotify too.
Yeah, just
This is
Spotify.
just Spotify too.
Crazy.
Wow. Yeah. Well, I mean, keep it up. Let us know. Let us know about suggestions. I mean, we're always open for suggestions.
Oh
you
yeah,
know,
100%.
here and there.
Wait, special relativity part 2, is that ever gonna come?
2. Yes. That will come out.
We need
in
the
my
prof. What
opinion.
about the
Yes,
prof?
exactly. I was just
Yeah,
okay,
yeah.
exactly.
Okay, let me say it. I emailed the prof here at U of T, and he emailed me back saying that, or to be more specific, he is a ex-professor of the general relativity course here at U of T, which is a 4th-year course. And he's not teaching right now. He's on a sabbatical, but he said that he has 30 years of experience of talking to the press about like science,
Wow.
like explaining science. So he said he said he'd come onto the podcast, and then I'm pretty sure I emailed him back, and then he didn't answer, and then I forgot to email him back again, and then this was in the summer. So I will re-email him, and then we will have special relativity part 2, which will be
special. Let's
yeah,
have
but
a
it'll be general. It'll be general.
Let's have a general relativity.
That'll be the
episode.
part 2 though.
That will be so insane.
Yeah.
A general relativity, because I mean, I think I mentioned this before, right? Like the quick presentation that I gave on field equations. Like, I mean, obviously, like the math was nowhere because I was in grade 11, and it was talking about general relativity. But like, just my interest, man. Like, I would love to talk to someone about general relativity. That would be really an experience.
Yep.
Yeah, so we can definitely get that prof on. We have a few more guests, I think, now that the school is a lot of stuff. You know, we just have to it's just stuff to do. So a lot of times we're just figuring out stuff. So. And just a lot of work. Even they have a lot of work on their part. So, you know, getting professors free in this time is a little complicated.
That is true.
So it is a little hard for all of us. And as usual, we're bang in the middle of midterm week. We're out here recording the podcast. So
Wow. That must have been a pleasant sound.
oh yeah, sorry, I apologize. But definitely continue to listen. Continue to follow. You know, wherever you guys do, we appreciate it. We appreciate all your comments, all your emails. Whenever we do get through them, that is. We do read them. I mean, clearly, I read every single comment. If I reply or not, sometimes it's because I'm doing something. There might be, okay, I'll give more time to reply to this. Sometimes I'm like, okay, I'll actually sit down and think about it later. But then that later just never comes because I just have stuff to do. You know what I mean?
I feel like we still have emails that we haven't answered.
No, maybe emails haven't answered, but I've read, and so have you, every single one, and every single I've read every single YouTube comment we've ever got.
No, that's true.
It's just that I haven't, because I'm not always just replying to everything. It's just that I see an email, I'm like, oh shoot, nice. You know what I mean? So many times. So I mean, keep them coming. We love to read them. We always do. And anything else?
I guess that's everything. Thank
Follow
you.
us on Insta. Oh, I guess here. Follow us on Instagram. math.physics.podcast. And
Yes.
if you want to email us, it's the same tag at gmail.com. Super simple.
Yeah. So
Let us know.
thank you so much for listening to this episode where we just talked about things.
Let us know how you like this episode. I want to know, because a lot of our episodes, again, are very, very, not very different, but different, because we have, again, some things to talk about. I really like this, though. This was so chill. This was just a cool conversation between things that we're interested in. Next time, if we ever do this again, it's going to be more statistics next time.
Okay.
You already know. So we're definitely going to have a little more fun in that in the future. But yeah, let us know what you think about this one.
Yeah, this has been episode number 83 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray. We will see you soon.
Bye, guys.